All right, so we're going to finish up chapter 7 today, and we'll be looking at 7.6. So we're going to be solving trig. We're going to be looking at some trig identities, solving them, looking at equations. We don't really look at inequalities. I think that was in the title of the section, so I just copied it, but it's really pretty much equations. So there's a couple techniques we can use to solve equations. Okay, one method is factoring. And remember, even with factoring, there's two different types. There's this type of factoring, where you put two sets of parentheses, and you write something like that. And then there's a simpler kind of factoring, where you just take out a GCF. Like in this case, you could factor out a 3 and an x. And have something like that. So both of those types of factoring might come up in this section. And the other method, we generally want to make sure when we're trying to solve one of these equations that we only have one trig function in the whole problem. If we can, we'd rather not have things mixed. This is an example of a problem where the trig functions are mixed. You've got sines and you have cosines. It would be better if we had just one or the other. Okay, so we're going to try to rewrite things using a single trig function. And once you get things written as a single trig function, you can also use the quadratic formula. It's pretty similar to what you're used to doing with quadratic formula, but there's a little difference kind of at the end. Because most of our trig functions, they're not going to be just a variable squared, it's going to be a trig function squared. So I'll explain how you deal with that. All right, so let's take a look at this. Now there's 3 different Pythagorean identities we've talked about. We're going to be using them today. I think those are probably the most important ones. Sine squared plus cosine squared equals 1. 1 plus tangent squared equals secant squared. And 1 plus cotangent squared equals cosecant squared. Those are the 3 Pythagorean identities. For this one, we need this one. So I put it up there. Now, whenever you have an equation, and it has more than one type of trig function in it, you always substitute for the one that is squared. That's how it works. You always substitute for the one that has the exponent of 2. What do you substitute? You have to look back at identities you already have in your notes. So this is an identity we did last week. Sine squared plus cosine squared equals 1. In the problem that I'm about to do, which trig function has the exponent of 2? Yep. The cosine. It's cosine squared. So what I want to do is substitute for cosine squared. I'm going to use the Pythagorean identity from last week, and I'm going to solve it for cosine squared. If you solve it for cosine squared, what would be on the other side? Chris?
1 minus sine squared.
1 minus sine squared. So that is what we're going to substitute in that box. So we're going to have 2. Whenever you substitute in something, it's always a good idea to put parentheses, just in case distributive property comes up. Everything else stays the same. But instead of putting cosine squared x, we're going to substitute what cosine squared equals using a Pythagorean identity. Cosine squared is 1 minus sine squared x. Now, I just mentioned this, but what property is going to come up with that 2 in front of those parentheses? Ashley?
Distributive?
Yeah, distributive. We have to distribute this out. So let's distribute it. We have 2 minus 2 sine squared x, and then everything else stays the same. Now, do I have any like terms that I could combine? Yeah.
The 2 and the 1.
Yeah, the 2 and the 1. And if you combine 2 and a positive 1, what do you get?
3.
3. So we're going to write negative 2 sine squared x plus sine x plus 3 equals 0. Now, that equation, what does it kind of look like? I think I asked you this question yesterday. It kind of looks like what other type of equation that we've solved before? Yeah?
Quadratic.
It looks like a quadratic, and it basically is a quadratic. Anything that has the pattern where you have 3 terms, and this exponent is double that exponent. It doesn't even have to be a 2 and a 1. It could be a 3 and a 6, or like a 6 and a 3, or a 4 and a 2. But anytime that this exponent is double that one, and you have to have the same function all the way through, like it's like having the same variable, sine and sine, yep. And the last number here has to be a constant, just a number. Anything that fits that pattern that I just said is basically a quadratic. So we can try to solve it with factoring, or we can use quadratic formula. If we're going to factor it, you'd be thinking about it like this. That's basically what you're trying to factor. The problem is this. All the factoring that you've been taught how to do is always when the squared term is positive. So if you want to try to factor this, you should make the squared term positive. What can I do in all 4 terms of that equation to make the squared term positive? Just take everything and, yep.
Divide by a negative?
Yeah, just divide everything by a negative. And that's going to turn it into 2 sine squared x minus sine x minus 3 equals 0. Now we're set up to try to factor it. Okay, let's see if we can factor it without changing it to like 2x squared minus x minus 3. Let's see if we can do it with the signs, and if we can't, we'll change it. Okay. Anyone think they could tell me what my first terms would be in each parentheses? Tyler?
2 sine x. And then sine x.
Sine x. It's exactly like writing 2x and x. Same thing. 2x and x, 2 sine x and sine x. Now we need to figure out our positives and negatives. Do I need 2 positives, 2 negatives, or 1 of each? Yeah?
1 of each.
I do need 1 of each, and it does matter which one goes where. If you're not sure when you're doing it, just maybe take a guess. Yep. We'll try that. And now 2 numbers that multiply to give me 3. Yeah.
1 and 3.
1 and 3. I'm going to try them in this order. 3 and 1. And let's see what happens. So we get 2 sine times sine. That's good. 2 sine times 1 is 2 sine minus 3 sine. 2 sine minus 3. 2 minus 3 is negative 1. Perfect. And negative 3 times 1 is negative 3. Okay, so that's the hard part. Now we factored it. Now from here, I think we did this problem yesterday, if you look in your notes, but we'll finish it here again. We have something times something equals 0. What do you do with each one of these factors? Yeah.
Set it equal to x. And 0.
Yeah, set them equal to 0. So 2 sine x minus 3 equals 0. Sine x plus 1 equals 0. And Matt, how would you get sine x by itself here?
Add 3.
And then?
And then divide by x. Oh, sorry, sine.
Well, we're trying to get this by itself. This is all glued together. You can't separate the sine and the x.
I'll take the inverse.
No, because all right, let's do this in 2 steps. Okay, now how would you still have to get sine x by itself.
divide by 2.
Yes, now divide by 2. And we've got sine x equals 3 over 2. Now we're ready to take the inverse sine. You can't do inverse trig until everything else is on the other side. Okay, let's take the inverse sine of each side. When you do it on the left, it's going to cancel. Do it on the right. And again, I think we said this yesterday too. What's the domain of inverse sine? What two numbers does it have to be between? Yeah?
-1 and 1.
Right. The domain of the inverse is the same as the range of the original. That's -1 to 1. 3/2 is 1.5. So when you try to take the inverse sine of 3 divided by 2, you're going to get an error that it's not in the domain. That means there is no solution from this part. Okay, so no solution there, but we still have to look at this part. Abigail, how would I get sine x by itself here? Yep, I'll subtract 1 on both sides. And Jack, what would I do now?
Can't think of the name. Sine -1.
Yep, inverse sine. So yeah, we're going to do the inverse sine. And again, the easiest way I think to figure that one out, I mean, you can use a calculator, but just think of the graph, and that's a special case. Where does sine hit -1? At what angle? Yep.
3 pi over 2.
3 pi over 2, or in degrees?
I don't have that memorized.
What's 3 pi over 2? Yep.
270.
270. So let's write both answers. 3 pi over 2, which is the same as 270. And that's it. It's your only answer. It's pretty rare to only get one answer to these problems. Usually you end up with more than one. But we had a no solution, which is why we only ended up with one. And this is a special case, so we don't have to do the ASTC thing, which would normally give us another answer. So a couple things happened in this one to just give you one. Questions on that? All right. Try another one. Pretty similar. This time, they're asking you to find all solutions in one period, versus last time, they just said to find all solutions between 0 and 2 pi. Well, this is one period, 0 to 2 pi. So that's what we're always going to use in these problems. We'll be going 0 to 2 pi. And remember, if you include 0, you don't include 2 pi because that's a repeat. That would be what you're going to do if you do it in radians. How would I write that interval if I was doing this in degrees? From what to what? Tyler?
What was the question?
How would we write that interval if we were doing it in degrees? Yeah?
It'd be 0 to 360.
0 to 360. Yeah, so we want to make sure we're pretty good with converting between degrees and radians. Maybe not something obscure like 17 degrees or something, but zeros, 90s, 180s, those ones we should try to be pretty quick at them. Okay, so 0 to 360. Let's do it in degrees. Okay, if we want to do it in radians after, we can, but I'm going to do this one in degrees. So I'm going to go 0 to 360. All right. So, does this look like a quadratic type of equation the way it's written right now? Not quite. A couple things wrong with it. First of all, to be a quadratic, what do we always get it equal to? Tyler?
0.
0. So let's just put everything on one side. It doesn't matter what side you put it on, but I'm just going to put everything on the right. You'll see why I'm doing that in a second. You could put everything on the left. It would result in one extra step. So we're going to have negative 2 sine squared x plus cosine plus 1. Now it's still not quite a quadratic. There's something here that's not good. We have to fix. What else do we have to fix in this one? Jack?
Divide by negative.
Well, you're going to see what happens in a second. I could have put this on the other side and kept it positive, but I actually made it negative on purpose. But you'll see why. And it has to do with the answer to my next question. So what do we still have to fix here? Yep.
It has a sine and a cosine.
It has a sine and a cosine. That's no good. You can't have two different trig functions. That's like a quadratic. It's like this. You get two different variables. That's not going to work. So we have different functions. Which one did I say to always substitute for? Yep.
The one that's squared.
The one that's squared. So we're going to substitute in for sine squared. Copy everything else down. Leave some space to fill something in. And let's think of our Pythagorean identity with sine squared. Sine squared plus cosine squared equals 1. So what could I fill in here for sine squared? Chris?
1 minus cosine squared x.
Yep, 1 minus cosine squared x. Questions on where that came from? All right. Now it's very similar to the last problem. What's my next step?
Distribute the
Yep.
-2.
We're going to distribute the -2. And Francesca, can you tell me what I get when I do that? Can you remind us, actually, what are we doing again?
Distributing
Distributing what?
the -2.
Oh, okay. So yeah, distribute the -2.
So it's what you do with -2, and then with cosine, and it would be -2 cosine squared.
I like the -2, that's good. But what would go right after that?
The cosine.
What are you multiplying next?
What is the x?
So you did this times this. Right? What are the next two things you're multiplying?
So you did the -2 times the cosine,
The -2 times the what?
the cosine squared.
I don't see a cosine squared.
Oh, the negative cosine squared.
So what's -2 times negative cosine squared?
+2 cosine squared.
So that's +2 cosine squared. Everything else stays the same. Okay. How about Zach? Do I have any like terms there?
Cosine x, and no, it's cosine squared.
Yeah, those are different.
-2 and 1.
-2 and +1. What do you get when you combine those?
-1.
So we're going to write 2 cosine squared x plus cosine x minus 1. Now, remember, some people were kind of worried maybe about that cosine squared being negative. Well, look what happened. It automatically isn't. Because when I changed sine squared, and then I distributed the negative 2, it took care of itself. So I didn't have to worry about dividing everything by a negative 1. Had you put everything on the left side, you would have ended up having to divide everything by negative 1. Not a big deal, but by doing what I did, I saved the step. All right. Now, from here, what are the two methods you can try to solve this problem? One of them works if the numbers are nice. The other method will always work, but we haven't done the other method yet. Chris, what's one of them?
The factoring.
Yep, we could do factoring, and that'll work if the numbers are nice. Or the other method we could use, yeah?
Quadratic formula.
Quadratic formula. Okay, that method will always work, no matter what. Let's try one more with factoring. So 0 equals. And what would be, let's see, what would be my first term in each set of parentheses? Yep.
2 cosine and cosine.
So we got a 2 cosine and a cosine. What about my positives and negatives? Both positive, both negative, or one of each? Tyler?
Both negative?
Well, if they're both negative, then I'm going to end up doing a negative times a negative when I do the last ones. And that's not going to give me a negative.
So one positive, one negative.
We have to have one positive and one negative. Let's try that way, see what happens. And Bailey, two numbers that multiply to give me 1.
1.
And?
1.
1 and 1. So let's see what happens. 2 cosine times 1 is 2 cosine. Negative 1 times cosine is a negative cosine. 2 cosine minus cosine is cosine. Perfect. So this was factorable, and we're done with the factor. Now, what do we do, Casey, what do I do with each of these factors? Yep, so when I set 2 cosine x minus 1 equal to 0, what would end up being on this side after you move the 1 and the 2? Yep.
1/2.
1/2. So you'd have to plus the 1, and then you'd have to divide by 2. So, we got that. Now, let's do the other one. Cosine x would equal 1 in that case. Yep. Negative 1. Now, cosine x equals negative 1. Well, I thought we did it. No, we did sine negative 1. Okay, so we gotta do that. Let's do that first because it's a special case. Remember, cosine starts at the top, comes down, and goes back. Anybody remember where in the cycle cosine hits its low point, negative 1? Chris?
Pi.
At pi, or in degrees?
180 degrees.
180, yep. And you wouldn't be asked for both on the test like that. You'd be asked for either degrees or radians in a problem. Okay, but I'm showing you how to do both. Okay, so we got our answer from this. Now we need to finish off this. Now, cosine equals 1/2. That's not a special case. Okay, that's something we're going to use the ASTC diagram for. So let's just think a little bit. Where are the two quadrants where cosine comes out positive? Yep. Can you just give me one of them?
1.
One. Can someone else give me the other one? Okay, 4. Okay. So keep that in mind. So looking for an answer in quadrant 1 and 4. All right, I want to get x by itself. Sarah, what am I going to do to get rid of cosine?
Take inverse cosine.
Yep, take the inverse cosine. And now we're at the point we're going to use the calculator and see what that is. So inverse cosine of 0.5 gives me 60 degrees. Now, the other answer we're looking for is in quadrant 4. This is a reference angle. Once you have a reference angle, what do you do with it to get an answer in quadrant 4? Yep, Tyler.
Subtract it from 360.
Subtract it from 360. And what is 60 degrees if you write that one in radians? I want you to know how to do that. It's basic convert degree to radians. What's 60 degrees in radians? Yep. 1.05. No, we want a dust fraction with pi. So that might be what it comes out to, but we're looking for something with a pi in it. Yep.
Pi over 3.
That's pi over 3. Now, you multiply 60 by 5 to get that answer. So multiply that by 5 to get that answer. 5 pi over 3. So there are all your answers to this problem in both degrees and radians. 60, 180, and 300. And double check that they're all between what we said they should be. And yeah, they're all between 0 and 360. That's originally what we said we had to do. Okay, questions on that one? So let's try, let's try this one. Does that look like a quadratic equation? It's going to end up being a quadratic. It's going to end up being exactly the same as the other two, except I think we're going to use quadratic formula on this one. Does anyone have a guess what we could change the left-hand side into? This is another identity we've talked about. And it's one of the basic tricks that we use sometimes when we're doing identities. Okay, one of the tricks is like rewrite with a common denominator. Well, we're not doing that. Another trick is to multiply top and bottom by the conjugate. Well, we don't have fractions. But it's the very first trick I taught you about identities. Yep.
Doesn't tangent of x equal like sine over cosine?
Yeah, change everything to sines and cosines. Okay, what's one of the first things that we learned about identities. So let's change everything to sines and cosines because we're trying to just get one trig function. And at least we can get a cosine over here, and we have a cosine over here, so maybe we're starting to turn it into something. So sine over cosine equals 3 cosine x. Now, the only thing I don't like about that is that it's a fraction. So what could I multiply everything by so I don't have a fraction here? Take
Cosine x.
Yep. Multiply everything by cosine x. And now, you should start to see it turning into a problem very similar to what we just did. Here, the cosines cancel. You're going to have sine x on the left, and you're going to have 3 cosine squared x on the right. Now, hopefully you can see it's starting to look more like a quadratic. What do we always get a quadratic equal to when we want to solve it? Sarah? We want to get it equal to 0. Anyone have a guess what side we want to put the, well, I already told you we're going to do quadratic formula. So if you're going to do quadratic formula, it doesn't really matter if the squared term is negative or positive. I mean, that doesn't matter. So let's, you tell me, Matt, you want to put everything on the left or you want to put everything on the right?
On the right.
Okay, we're going to put everything on the right. So then we're going to have 3 cosine squared x minus sine x. Too many 3's. Now, there's just one thing wrong with that from it being a quadratic the way we're looking for. Abigail, what's still wrong with that? Well, what if I gave you a quadratic to solve and it looked like this? We need what? Yeah, we have like a y and an x. We can't have 2 different things, and that's what we have right now. So we got to get rid of one of them. Well, what's the one that we always substitute for? Yep.
Oh, the square root.
The one with the what?
Yeah, with the square root. So the square
With this?
Squared.
Square. I know what you meant. So we always substitute for the one that's squared. And I think we've already substituted for cosine squared before. Can somebody remind me what you get when you substitute for cosine squared? Matt?
1 minus sine squared x.
Perfect. 1 minus sine squared x. Now let's use our distributive property to multiply it out, and let's also rewrite it the way we would normally write a quadratic. So I'm going to distribute that 3. 3 times 1 is 3, but I'm going to put that at the end. That's my constant. 3 times negative sine squared is negative 3 sine squared. Not how I would want it if I was going to factor it. But we're going to use quadratic formula, so that's okay. And then minus sine x. And that's a plus 3. Now, that's a quadratic. Didn't look like a quadratic at all when we started it, but it was. This isn't factorable. Okay, so let's kind of look at what's happening here. If this was your problem, what would you be solving for if you use quadratic equation on that? You're solving for what? Yeah?
X.
You're solving for x. More specifically, when you use quadratic equation on a quadratic formula on a quadratic equation, you are solving for whatever is in the middle. It could be an x, it could be a y, it could be a sine x. So you're always solving for what's in the middle. So if you were doing this problem, this is what you'd write. X equals, and then you do the quadratic formula on that side. Well, we're not going to write x equals and do the quadratic formula because we don't have an x in the middle. What do we have in the middle in our problem? Yep.
Sine x.
We have a sine x. So we're going to write sine x equals. And now we're going to do the quadratic formula on the right-hand side. So what does that mean? At the very end, you need to take inverse sine to get rid of it. Right, but that's That's the only difference with using the quadratic formula here. Take what's in the middle and set that equal to your quadratic formula. All right, now let's do it. Let's identify first A, B, and C. Casey, what's A in this case? -3. And Ethan, B?
-1.
-1. And C, Chris?
3.
3. Okay, so let's go through the quadratic formula. Put that on the other side. So we got -b plus or minus b squared minus, and Francesco, what comes right here?
3. Or -3.
Well, it's something times something. You have to multiply 3 things together.
Isn't it? Oh, -1.
Minus what?
-1.
Well, it starts out with a 4.
Oh, 4, and then it's AC, right?
And then it's AC. So we got that. All over -6. All right, so sine x equals, what do you get under the square root when you do that out? Yep. 37. These cancel, becomes a plus. 4 times 3 is 12, times 3 is 36. 36 plus 1 is 37. So hopefully you can see now, this is why you couldn't factor it, because it doesn't come out nice. All right. And remember, this plus or minus means you're getting 2 answers. Okay? A lot of times people forget when you take a square root, you get the plus and the minus. People don't forget that as much with the quadratic formula because they just remember it's part of the formula. But let's separate it out. So sine x equals 1 plus root 37 over -6. And sine x equals 1 minus root 37 over 6. And in both of those equations, what am I going to do to get rid of sine?
Take the inverse.
Yep, I'm going to take the inverse. So let's do 1. I just want to see what this is first. 1 plus the square root of 37. 1 plus the square root of 37. And I'm going to divide by -6. That's -1.18. I want to take the inverse sine of -1.18. What is inverse sine supposed to be between? Yeah?
-1 and 1.
-1 and 1. So this has no solution. Because this is -1.18. So if you try to take the inverse sine of all that stuff, you can't do it. It's too big. Well, it's too negative. So no solution from this part. The other part, I think that's going to be fine. So let's do 1 minus the square root of 37. So that's the numerator, divided by 6. Divided by 6. That's fine. That's -0.84. That's definitely between -1 and 1. I can do the inverse sine of that. So let's do it. So I'm doing inverse sine of what I just typed in. You can just press second answer so you don't have to type that decimal all over again. And we get -57.90. All right, now, scroll back up for a second. It said the answer, let's just to do it the way we did it, we said, let's make that 360. It said the answer was supposed to be between 0 and 360. Is that answer between 0 and 360? Then we need to make it between 0 and 360. What can you add to any angle? Or subtract if you need to, but we need to add here to make that a positive. Yeah?
360.
You can add 360 to it. 302.01. There's nothing wrong with that first answer we got, other than it's not between what they said they wanted. So we had to add 360 to it. Now, when I did that out, 1 minus the square root of 37 over 6, I got negative 0.847, roughly. So all of this was about negative 0.847. You're looking for where sine equals a negative number. Can somebody give me one quadrant where the sign is negative? Tyler?
The second quadrant?
Which one?
The second?
That's where it's positive.
Third?
The third. And where else is sign negative? Yep. The fourth. Where's 302.01? It's got to be one of those. Yeah. Fourth. So we have the answer here. Now, question. Is that a reference angle? No, reference angles have to be in what quadrant? Yeah.
1.
Quadrant 1. So we need to do this. That's what you need to figure out now, because you need the answer in quadrant 3. But you have to figure out what the reference angle would be. Well, you know the answer in quadrant 4. The formula for quadrant 4 is 360 minus your reference angle. Well, the answer in quadrant 4 is 302.01. So figure out what you would subtract from 360 to get 302.01. That's your reference angle. So we can just figure that out. 302.01 equals 360 minus my reference angle. So just bring the 360 over to the other side. This usually doesn't happen where you have to figure out your reference angle like this. It's kind of a special situation that this came up. But it's not that hard to figure out. So my reference angle is 57.90. So if you take 360 minus 57.90, you would get 302.01. We actually saw that number earlier. That 57.9, it's actually still on the screen. So I kind of knew that already was going to be the reference angle, but if you didn't know that, that's how you could figure it out. All right, so now we got our reference angle. Now, do that. You're looking for an answer in quadrant 4. So 180 plus the reference angle. And that's the other answer that I need to put in that box. Can somebody tell me what that comes out to? 180 plus 57.9? Tyler?
122.1.
What is it?
122.1.
Well, it's 180 plus 57. So it's got to be bigger than 200.
Isn't it a negative 57?
No. The reference angle is a positive 57.
237.9.
What is it?
237.9.
237.9. Okay. So again, a little weird because we ended up with that situation where we had to figure out the reference angle. Sometimes, usually you get it right away just by doing inverse trig, but this time it didn't quite work that way. Okay. Yeah.
Would this be on the test?
this solving a problem with quadratic formula?
No, where you have to add, where it's not in our, it's not in our, it's not in our, final reference table here.
It's not, so what specifically are you wondering?
Like, if we get an exact answer instead of like a reference table. Basically, the reference table, that's what I'm asking for.
Like if you needed it as an exact answer?
Yeah.
No, decimal's fine. Yeah, decimal's fine in this one. Because it's not a nice enough problem because it's quadratic formula. Whenever you use quadratic formula, assuming you couldn't have factored it, you're never going to get a nice answer. So you can always just round it off. Two decimal places is fine. Yeah. Any other questions on that? Alright, let's see. Just skip one of them. This is kind of the same as the first three. It's another quadratic type problem. You get everything on one side and then you substitute for cosine squared. You wouldn't do anything different here that we haven't already done. Let's do this one. Maybe we'll do that one, and then maybe that one. We'll see. All right. Now, in this one, the trig functions are the same, sine and sine. But there's a problem here. Does anyone see what the problem is? Tyler?
And 2 is behind the sign.
Yeah, not only do the trig functions have to be the same, but the arguments to them have to be the same. If the arguments aren't the same, the whole thing blows up. It's no good. So we gotta get rid of that 2 in front of the x. And we have a formula that gets rid of the 2 in front of the x in a sine function. Does anyone remember what you can substitute in for sine 2x? And I don't want to do sine x plus x. We've done that, and then we figured out what that comes out to. That's what I want to know. Jake?
2 sine x times cosine.
Yep, that's 2 sine x cosine x. Now, you might be thinking at first, well, that's now worse than what we started with. Now we have 2 different trig functions. Well, you had to do it. You had to get rid of that 2. So if that's what happens, that's what happens. All right. Now, we want to try to do this like we've done before. What do you think we want to get it equal to? Yep.
0.
0. And Jack, how would I get that equal to 0?
Minus the sign x.
Yeah, let's just put the sine x on the left. That's the simplest way. That's the least amount of stuff you got to move. So minus the sine x. So you're going to have 2 sine cosine minus sine. What can you do, or if you look at those 2 terms, there's something you can do there that I talked about. This is the first time we've seen it today, but I said it would come up. Yep.
You pull out sine x.
Yep, pull out a GCF. It's the simple kind of factoring. Just take what they have in common out, and then you're going to be left with something that's just like what we've been doing. Pull out sine x. And Chris, what do you have left if you do that?
2 cosine x.
2 cosine x.
Minus 1.
That's a time symbol. So you have 2 sine x.
2 cosine x, not sine.
Yes, cosine x. Thank you. So you pulled the sine out. And now when you take the sine out of here, what did you say?
Minus 1.
Minus 1. Now you've got something times something equals 0. Set each factor equal to 0 and solve. So either this factor is going to equal 0, which would be a special case. We'll draw a picture. Or cosine x would equal, what would go on the other side? Sarah? If you had this, it would be negative a half. but you're gonna have to add the 1 and then divide by the 2. So when you add the 1, it's gonna become positive. So it's positive 1 over 2. Now I know we've done that today. Cosine x equals a half. We did it somewhere. Was it this one? This one. Yes, cosine x equals a half. 60 and 300. So I'm not going to go through that whole thing again. You can just look at the video and watch how to solve it all over again. But 60 and 300. All right, so let's write that down. 60, 300, pi over 3, 5 pi over 3. And now sine x equals 0. I don't remember if we've done that one today. I don't think so. But again, when sine is equal to 1, negative 1, or 0, that's a special case. So draw your sketch. And where does the graph of sine hit 0? In the interval from 0 to 360, not including 360. About Casey?
0, 5.
Yep. Hits it at 0, hits it at pi. If you're like, well, what about here? No, don't include this one. Because it has a parenthesis on the 2 pi. Alright, so x equals 0, and you said pi, what's pi in degrees?
180.
How much?
180.
Yep, 180. So pi and 0. Alright, so there are the 4 answers that you get from that one. It's a little different because it started out with that 2, but once you use the double angle identity, just basic factoring, no quadratic formula or anything in this one. Okay, questions on that? Okay, so that's pretty much the idea of 7.6. All right, now for the homework, let me double check something.
I'll do it.
Okay. Now, in 1 through 9, what they do is they start you off in the problem at this step. So they've already done all the work right up to the factor. So it's not like 9 problems we did in class. They're starting you 3/4 of the way done. So it's a lot quicker. But then, let me see. We'll do 11. 13 is good. 14, we'll skip that one. And then 16 and 19, we'll skip that one. So it's 1 through 9, 11, 13, and 16. All right, so we'll take a look at those tomorrow.